Now let us consider the derivative of a function when some expression is raised to a general power. Up to now, we have seen a few simple rules how to differentiate. We have seen that a derivative of a sum is sum of derivatives, derivative of a difference is difference of derivatives, derivative of a product is not product of derivatives, but is given by this formula, u prime v plus uv prime. And similarly for the ratio, for the fraction, derivative of a fraction is a fraction in this form. We have also discussed the derivative of the composed function. U composed with v is the product of the derivative of the outer function times the derivative of the inner function. This rule is sometimes called the chain rule. But now, what if we have two expressions where one is raised to the power of the other? Not to be confused with cases when the exponent is constant. When the exponent is constant, we have the formula n x to n minus 1. Possibly, if the base is not x alone, and it is some expression u of x raised to the nth power, derivative of that will be similarly n times u of x raised to the power of n minus 1 times, because this is a composed function, u prime, the derivative of the inner function. And also, this is different from the case when the base is constant. We have seen that e to x derivative is e to x. We have seen that the general base a to the power of x derivative is this function a to x times logarithm of a. Actually, instead of x, we can have any different function. So if we have e to u of x, derivative of that, then this is the function itself times the derivative of the inner function. But still, this remains open. How to differentiate when both the base and the exponent vary with x? There is a good formula that any positive expression can be written as e to logarithm a. And then we can write that u to v, and for such expression, when u is a y function and v, we assume that the base u is positive. This is our condition to make things simple. We always consider base to be positive when we have general base and general exponent. So this can be written as e to logarithm u to v. And then logarithm u to v can be written as v times logarithm of u. All the time assuming u is positive. In full notation, instead of u, we should write u as a function of x, and instead of v, we should write v as a function of x. But a function may be as well a constant, right? So this will be a good transformation to compute the derivative, because if we differentiate this, then this is the way. Now we have the constant base. So this derivative is the function itself, e to v logarithm of u times the derivative of the inner function. The inner function is the exponent. This is a product. We use the rule how to differentiate a product. This is derivative of the first times second logarithm of u plus, we copy the first times, and we differentiate logarithm of u, which is 1 over u, times the derivative of the inner function, which is u derivative. And that's all. Well, let's practice this for expression like x to x derivative. So first we can write it as e2 logarithm of x to x derivative. Then we write this exponent in front of the logarithm, and we have e2x times logarithm of x derivative. And now the derivative of the exponential function is the function itself, e2x times logarithm of x times the derivative of the inner function, which is the exponent. This is the product. Derivative of x is 1 times logarithm of x plus x times 1 over x, which is 1. And we are done. And for this to make sense, the condition is x must be positive. So at this point, we have all the rules to differentiate any function. As a surprise, integration, that is the reversed operation to differentiation, is not possible to do for any function. But we can differentiate, we can compute derivative for any function written using plus, minus, and so on.